Welcome, everybody. This is the Fast Code Seminar, and today's talk is one in a monthly series of virtual talks on the latest topics in the theory, practice, and teaching of software performance engineering. My name is Bruce Hoppy. I co-chair the organizing committee for the seminar, and I lead community outreach for the larger Fast Code project of which this seminar is a part. Christian is going to introduce our speaker in just a couple minutes. But I'd like to take just a moment to let you know about the Fast Code seminar at large and the Fast Code project. I'm going to paste a link into the chat so that if you like, you can see the Fast Code website, which I'm going to share on my screen. Okay, hopefully everybody can see my screen right now. Fast Code is an open source community dedicated to advancing software performance engineering. And our website is where you can get started learning about that and sharing with other folks who you think would also be interested. The seminar is one of our featured events. I'm going to scroll down so that you can see we have a couple others. And let's take a look at the Fast Code seminar. Algorithms, compilers, accelerators, whatever it takes. And Renato's giving today's talk after today. We're taking a little break in the month of August, then we're going to return. And we have Goju Gachlich in September and Rich Vodek in October scheduled to give talks, and we'll be continuing monthly. You can also see previous seminars, and we've got videos for the last 3, and we'll be continuing to record and share those. And I want to thank everyone listed down here at the bottom, the whole organizing committee that make these seminars possible. Jacob and Roberto and Christian and Julian and Yihan. If you have a suggestion for someone who would be a good speaker for a Fast Code seminar, please let us know. In addition to the seminar, we have other things happening. One of those is a Fast Code blog, which is hosted on Substack. If you have any story that you would like to share, we would love to help write about it on the Fast Code blog, and I'd be delighted to hear from you. I also want to mention one other thing that's happening, which is we have a special session scheduled for HPEC. It's a virtual conference happening in September. And so I invite you to save the date, September 15th, 19th, and we'd love to have you attend our special session on task parallel technology for software performance engineering. So with that, I'm going to turn it over to Christian for introducing our speaker.
All right, thanks a lot, Bruce, for the intro. Well, good morning or afternoon, depending on where you are, everybody. It's my pleasure today to introduce our speaker, Renato Werneck. Renato is a senior principal scientist at Amazon currently, where he leads research in modeling and optimization for last mile deliveries. Prior to that, he has been at Microsoft Research in Silicon Valley. He contributed a range of fundamental advances in graph algorithms, data structures, to practical systems for transportation networks, including routing engines and optimization tools used in products like Bing Maps or Amazon's logistics platforms. Renato holds a PhD from Princeton University, advised by Robert Tarjan, a master's from PUC Rio, and a bachelor's degree from computer engineering from Unicamp, where he graduated with the highest GPA ever recorded in the program. Having said that, please join me in welcoming Renato. I'm looking very much forward to your talk.
Thanks, Christian. Thanks, everybody, for inviting me. I hope everybody can see me and hear me all right. And with that, I'll go straight to the talk. So let me share my screen, which will help. So. Can you see my screen?
Yes, looks good.
Okay. So I'll talk about last mile deliveries at Amazon. As Christian said, I'm a senior principal scientist here at the modeling and optimization team, and I joined 10 years ago, always working on this space. So I'll talk a little bit about kind of what makes this space interesting uh, in the context of performance optimization and beyond. So a little bit about what do I mean by last mile deliveries at Amazon. So AMZL, Amazon Logistics, is Amazon's internal carrier, internal provider. So when you order a package at Amazon, um, you get it delivered to your home through USPS or UPS or DHL or Royal Mail, or depending on whatever you are, you get from a different provider. And a potential provider that you can get is AMZL. So these are, in many countries, these are these kind of gray, blue Amazon vans that deliver straight from Amazon using our internal capabilities. There are hundreds of delivery stations worldwide that deliver to final customers. They're organized by AMZL, and our job is to create the routes to make those deliveries. So the basic setup here is that you have these delivery stations. The delivery station will be kind of near typically near a major metropolitan area. The shipments will arrive from a fulfillment center or from a sort center overnight in large trucks and 53-foot trucks. So think of a container-sized truck. These are line hauls that will come with the shipments overnight. And then in the morning, we dispatch the actual routes. So these will be routes that may have like a few hundred shipments, maybe typically 200 shipments, that will leave from the delivery station and arrive in individual apartments, individual homes, individual businesses. And our job is just to create the routes that are used for those deliveries. AMZL is a very fast-growing business. So when I joined 10 years ago, it had just started. We basically were just making deliveries in the UK. So it was a very small business that was doing only part of the deliveries in the UK. And right now, it does the majority of Amazon deliveries in the US, does the majority of the deliveries in many European countries. It's also in some countries in Asia, in South America, in Central America, in the Middle East, and so on and so forth. And that all happened in a decade. So from Amazon making all of its deliveries through third parties to making the majority of its deliveries using this internal provider, which is AMZL. So as you can imagine, this is just creating routes for delivery. So we must solve some version of what is the well-known vehicle routing problem, or VRP. So we're given a set of shipments, we're given a set of vehicles. These vehicles have certain capacities, and our goal is to decide which shipments go into which vehicles, what is the route, what is the sequence of the shipments within the vehicle, and you want to minimize some notion of total cost with the routes that we create. So when I joined Amazon 10 years ago, I said, oh, cool, I'm going to get to work on this very large combinatorial optimization problem. I have a background in algorithms engineering, so I say, oh, like I just have to find the most efficient solution to this very hard problem. And I imagine at Amazon it will have massive scale, so there'll be a very it will be a very good match for my skills. And like I wasn't disappointed, so that's exactly what I found. It's a very large problem. It's very hard to solve. I have to apply like all the optimization and performance techniques that I can. But in this talk, I'll talk about what surprised me. Like, so that solving the problem wasn't actually the hard part. It turns out that that's only part of what I have to deal with and part of what my day-to-day is. Defining the problem turns out to be extremely challenging. So deciding what is the problem that you have to solve. There are like multiple inputs, multiple trade-offs, multiple processes. Even a human element plays a big role in like addressing this entire problem that we need to solve. And I think there are very, very important lessons that came from this. And I want to talk a little bit about this. In particular, the attention to detail of, given the density that we have, that all the simplifications that we're used to making when we're solving a problem in the abstract, we cannot make it when solving a concrete problem that will actually lead to a physical process that will have to follow that the solution to that problem. So assumptions in simplified models start breaking. So I will talk about performance after I talk about all those things, but like the emphasis will be in these kind of aspects outside of performance, and then I'll try to tie this down with performance itself. So I expect this to be a little bit different from the talks that we usually have in this series of seminars, but I hope you find it interesting, and there will be some good questions about this. So let me start with some of the challenges that we have. So when in the previous slide here, I was just I had an example of a typical vehicle routing, capacitated vehicle routing instance. That was an instance from a paper that I was part of in 2006. Back then, this was one of the largest instances that could be solved to optimality. And what you see here is like each point is a delivery that you have to make. The numbers are the capacities, are the demands in each one of those deliveries. In this case, you have a certain number of vehicles that are available. Each vehicle has a capacity, and your goal is to find a solution that, with that number of vehicles, that minimizes the total distance traveled. So it's a very simple problem, like to state. These are points on the plane, so the distances are just kind of Euclidean distances between these points, and you can make all these. You can apply all sorts of techniques to try to solve this problem. And just to be clear, this was the largest instance that could be solved at a time, one of the largest instances, and you had like 101 shipments that needed to be solved. Just in terms of order of magnitude, typically on a very large station at Amazon, we're going to have to deal with about 100,000 shipments. So it's a different scale of the kinds of problems that we need to solve. So, and the problem is more complicated than what the idealized version of the problem that you normally see is. Even the notion of, well, we have a bunch of shipments, you have to deliver to these shipments. So how do you translate the shipment to a location in the real 3D space of the world? So a location is typically defined as an address, like someone would tell you like 123 Main Street, or in some countries, an address like the red house next to the school behind the church is a perfectly fine way of defining an address. And we'll have to basically translate that address to a geolocation, so to a lat long in the real world. And more than that, we actually have to map that lat long to a position along the road network, because we actually have to get people to drive to that location, assuming you're solving the problem for driving. That can be more complicated in that direction too. And even that is not really well defined, because kind of if you look at a very simple case, you have a house on a two-way street. You actually have two different ways of approaching this house. You can approach from the same side of the street. In this example, if you're driving from east to west, or you can approach from the opposite side of the street. If it's a local street that is safe to cross, you may want to park on the opposite side of the street, then cross the street to visit the house. So even that one shipment, that one address, actually has two potential locations that you can drive to. And then from that location, you go to the next location, and depending on whether you came from the same direction, or whether you're going through the same direction or you're taking opposite directions, you may have to make a U-turn. So even the distance between two locations depends on how you park on one location and how you approach the other location. So it's often convenient to think of vehicle routing as, oh, you just have to solve a bunch of mini traveling salesman problem, one for each route. Even that is not even true once you're talking about the real world. if you want to simplify in that way, you still are solving a version of what we call the group TSP problem, in which each shipment actually has one or more options of like locations that are associated with that shipment. In this example, there's each side of the street. You can actually have, like, if it's next to a corner, you can have multiple multiple options there. And your job when creating the route is to decide not only the sequence, like which shipments go to each route and the sequence of shipments within each route, but also which side of the street do you pick for each one of those shipments that you visit. And of course, you can do things like dynamic programming for a fixed sequence to actually find what is the best side of the street that you're going to pick. But that's just one example of the level of complication that you get once you start looking for everything that happens in the real world when solving these kinds of problems. And of course, although you can cross the street and you can make U-turns, those are things to be avoided if possible. So that's part of your optimization function to decide like how to balance this across against other objectives that you may have. Even if we know where we're going, like what are the locations that we need to visit, now we have a job which is to decide how many of those shipments to put in each route. And that brings the question of like what fits in a route. Like ideally, you would like to put as much as you can in a route, but there are all sorts of constraints on how much we can do. So one of the main constraints is like how much time is spent on a route. So the more shipments you put on a route, the more the driver would take to deliver those shipments. And of course, the driver has a fixed shift time, so you cannot exceed that. And what would determine what the driver, how much time the driver would take in a route will be some combination of the transit times, like how long does the driver take to drive from each location to the next location, and service times, which is like how much the driver spends at each location. And that depends on the location. So in this picture here, there's a driver delivering to the front porch of what looks to be a suburban location. That's usually very quick. You just go deliver to the front porch. Sometimes you don't even need to wait for the customer to be there. You can just leave the package. If you're accessing a very large building, you need to get access codes, or you need to talk to the reception, and you need to go to individual apartments in the building and so on and so forth. All those things take more time. So we have to learn what is the time for each particular address that we should expect a driver to take. An additional challenge that comes with that is that the context changes. It's not like every driver would take the same time at every address. So drivers that have different levels of tenure and experience. For example, if a driver has just started making deliveries, like as a career, that's the first couple of weeks, we should not expect that driver to have the same level of performance as an experienced driver that has been delivering for months. So even for a driver that is experienced, the level of familiarity of the driver will influence how fast they can be. So if you have been delivering to the same neighborhood over and over again, you kind of know your shortcuts, you know how to access a particular building, you know how to where to leave the package securely, and so on and so forth. So all else being equal, you kind of expect drivers that are familiar with the area to deliver faster than drivers that are not familiar with the area. You can have more than one person in the vehicle that is making deliveries. So if the same driver has to park and then exit the vehicle and deliver the package, that will take a certain amount of time. But if there's a driver that is just driving and there's a second person that is getting out of the vehicle, delivering the package, etc., the total time to deliver the package will be different. Even time of day will influence like how long the route will take, depending on where you are at different times along the day. So if you are in an area where there's a lot of traffic, of course, you're going to take longer driving than at a different time where there's less traffic in the area. Weather will influence the time that the route takes, not only for driving, but also for like walking outside the vehicle. If you're in snow, you're going to walk slower. If there is too much heat, you want to walk slower so that things are safer as a driver. And that's just for time. So that's one of the potential things that may limit how much work we can put in a route. There are many other factors to consider. One of them is the volume, is the total volumetric capacity that is occupied by the packages in the vehicle. For whatever reason within Amazon, volume is actually used to refer to the count of packages, and cube is used as a word to define the actual physical volume of things. So we use cube internally to refer to that. Another metric is kind of weight, like how much weight all the packages in the vehicle fit. Some vehicles, particularly in central areas in Europe, they do have like a small capacity because of local regulations. There's sometimes you may limit the number of shipments. Sometimes you may limit the number of stops that are in each route. So like in if you have multiple packages that go to the same house or to neighboring house, you want to merge those packages into a single stop and then like drive once, park, and then deliver to all these packages in that same stop. There's a little bit more walking there, but it's more efficient overall, and drivers will like that. There are considerations of time windows. There's consideration of the distance driven. There's the consideration of battery range. So we're electrifying our fleet right now, and that, depending on the geography that you are, may be the limiting factor for like how far you can send the van and how much work you can put in the van, because after a while you're driving beyond the battery range of the van at that point. And the important thing is the binding constraint will actually differ within the plan. There will be some routes that will be limited by time, some routes that will be limited by battery range, some routes that will be limited by the cube capacity, and so on and so forth. And these are all things that we need to consider when doing the optimization.
Renato,
Go ahead.
if you don't mind, I'd like to just ask a kind of
Sure.
a question.
Mhm.
You introduced by saying you were surprised that these details are what became most interesting to you, if I heard you right.
Yes.
And I'm kind of curious, and maybe you're already headed to this point, in which case you'll get there. How were these details, like so many details, how were they revealed to you? And what was the process like of you're actually becoming interested rather than annoyed by all these details?
I'll get to that. Like, so
You'll get there. Okay.
Yes. The short answer is they were introduced with time. So basically what happens is we start optimizing for the simpler problem, and then there are escalations, and there are people that complain like, oh, you're not considering this, you're not considering that, but we should keep adding this and that and that. So I'll get to that in more detail, but I think the main challenge is the problem is never finished. Like, so every day there is a new requirement, and there is a new something new that people discover that is important, and that we should be considering when doing the optimization that we need to make. But this will be the theme of the next few slides. And if I don't answer, please ask again.
Very.
Okay. So I mentioned before that the binding constraints differ within the plan, and this brings us to the next step of this, which is the notion of heterogeneity and variability, which is actually, even from an optimization point of view, is what makes the problem like really hard today. So basically, each plan by itself, like the entire route plan, is very heterogeneous. So in the example that I gave before with the idealized problem that is solved in the scientific literature, it's a single type of vehicle, a single type of driver, everybody has the same capacity, etc. That's absolutely not what happens, at least with like Amazon setup and MZL setup. So the same plan will have lots of different kinds of vehicles, will be tens of different kinds of vehicles with different capacities. Like, so you have small van, large van, you have personal cars, all those things that kind of go into the same plan, and they have their own capacities, their own constraints. And you even have different driver capabilities. There are some drivers that can do some sort of deliveries, but not other kinds of deliveries. And we also have pickups. There's some constraints to what some of the drivers can do and some of what the drivers cannot do. There are different, even for the same type of vehicles, you may have a different departure times. So remember that we're planning for Like a typical example would be you have maybe like a typical large example would be you have 100,000 shipments and you're going to split them into a few hundred routes. So you have a few hundred routes that are dispatching. You cannot dispatch them all at once. Like there's a physical process in kind of loading the van, etc. That's what this picture is showing here. And you typically have a capacity to dispatch maybe 20 or 30 vans at once, and then you dispatch the next 20 or 30 vans, etc. And this would take a few minutes to dispatch each one. So for a single plan, you may plan for routes that dispatch over a period of a few hours, so of like 2 or 3 hours. So, and when considering the routes, depending on when the route dispatches, you're going to have different traffic conditions. You're going to hit a different points in the routes at different times of the day. So you have to worry about time windows, etc. So when creating the routes, you have to keep these departure times into account. We also have different what are called delivery service partners. So Amazon doesn't make the deliveries directly. What Amazon does, it works with local businesses. Those are called DSPs or delivery service partners, which are small companies that have their own fleet that they manage and their own drivers that they manage. So a typical station will have multiple of these DSPs, maybe think of 10 different DSPs. And while they're all capable of delivering to any area within the jurisdiction of the station, in general, they kind of they prefer and to kind of feel like they're responsible for a certain part of that jurisdiction. So if you have a station that is responsible for a certain area, you typically split the jurisdiction into sub-jurisdictions, and each one of these sub-jurisdictions is a preferred area for each one of these DSPs. Of course, we can have the flexibility depending on like how much capacity we have from each DSP on any given day to send them slightly outside their preferred area if that's the best way to serve the volume that we have. But if we send a driver very far from what their preferred area is, that will be a concern. So when doing the optimization, we do have to consider the preferred areas of each one of these DSPs separately. And that's at a company level. Each one of these DSPs may have tens of drivers, but we also consider each driver individually as well. So as I mentioned, like the driver will feel more comfortable and will be more efficient if they're delivered to areas that they're already familiar with. So when creating the plan, we don't create generic routes. We create routes with specific drivers in mind. Of course, downstream from planning, people may choose to switch the drivers if they want. But like by planning with specific drivers in mind, we can make sure that we create routes in areas that the driver will be likely familiar with. We also have to consider driver tenure when we create the route. So if a driver is just starting, we want to create a shorter route for that driver because we know they will not be able to kind of deliver a full route, and we want them time to basically train and be able to develop their full capabilities before they get a full route for them. So this is within a plan of a single station. Once you go across different stations and across time, there are also differences as well. So no two plans are the same. There's a lot, even within the same station, there is variation across the week. Like the distribution of packages that you get during the weekend is different from the distribution of packages that you get during the week, during weekdays. Even the distribution of packages that you get on a Monday will be different than the distribution of packages that you get on a Friday. And even the total number of packages will be different during the week. There's a normal weekly fluctuation of the volume. There's weekly fluctuation across different seasons. So we have famously, Amazon has a peak season where it hires a lot more people in order to handle in the US, handle the volume between kind of Thanksgiving and Christmas, and other countries also have peaks often during that time as well. But India, for instance, has like multiple peaks during the year, and we have to account for that. And there's also variations, a variation that happens across time. As I mentioned, AMZL has been growing very fast since the beginning. So it is common to expect that whatever happens in one year will exceed the volume and the density that we had in years before. So that's something that we have to deal with. Like our algorithms have to be flexible enough to handle those things. There are differences in geographies. Like sometimes even the same station will deliver to areas that are areas that are dense and areas that are sparse. So we have to make sure that whatever algorithms we come up with can handle these areas. So for instance, I'm here in Santa Clara in the Silicon Valley. This is a mostly suburban area. So there's a certain kind of deliveries. I live in San Francisco, which is a much more urban, much more dense areas, and like parking is a lot more complicated there. So the algorithm has to handle both of these. And in nearby, there's a station that serves Napa Valley, which is kind of an hour away from San Francisco, and it's rural. Like it's a completely different thing. So we have to make sure that whatever techniques and algorithms we come up with kind of can adapt and handle all these things, all these differences in a natural way. And this is all like all that I talked about within the Bay Area here in California. But like if you start looking at the difference between countries, they're much bigger. So we also deliver in the UK, we deliver in Germany, we deliver in Italy, we deliver in Japan, we deliver in Brazil, and each one of those will have their own constraints. For example, in the US, a lot of the deliveries are unattended. You can just leave stuff on the porch. Even in the UK, that's not true. Like, so there are most of the deliveries will be attended. So the driver is supposed to contact the customer or a neighbor or someone and deliver the package with someone. And there are also different businesses and different objectives. So like we have the high volume business, which is AMZL. Again, volume is response to the density and the count of shipments that we have. But we have another business that is AMXL, which is delivering heavy and bulky items, and those will have a different profile of what they want to accomplish. Even within the AMXL deliveries, we have pickups, we have lockers, and we have all sorts of special cases that we need to be able to handle in a way that works well for everybody involved. So now I'll get to like what was probably the most surprising thing to me, that coming from an algorithmic engineering background, I didn't think about it at all before I joined Amazon. And then after I joined Amazon, I said, oh, of course, this is extremely relevant. I don't know how I didn't think about this before. We talk about this, when we talk about these combinatorial optimization problems, we're talking about very abstract problems, right? Like, so we'll have a set of shipments. You have to partition these shipments into routes, and you have to sequence each one of those routes. But when you think about what is the physical process that happens, so like in the example that I gave, the station gets 100,000 shipments from upstream, from like using these big line hauls. Imagine that you have a pile of 100,000 shipments somewhere. And then the algorithm goes and says, okay, these 100,000 shipments actually have to be split 500 ways into routes with 200 shipments each. There's a physical process that is involved in kind of making this translation of a pile of 100,000 shipments into 500 piles of 200 shipments each. So, and physically sorting these parcels, these shipments, from the line hauls where they arrive into the individual vans can take hours. So literally it can take like 10 hours for you to do the end-to-end process of this. So how do you handle this? Like the first thing you can think of, the simplest thing is, well, you have an idea of what shipments are coming into the station. So before they actually come to the station, you use these shipments, you create your routes, and as the shipments start arriving at the station, you already know which route each shipment should go to. So you just have whatever physical process you have to basically, as soon as the package arrives at the station, you start moving this towards the van or an area that corresponds to the van for that particular shipment. The problem is you only have an idea of what's getting into the station. So even if you had perfect information of what is it in each line haul, in each big truck that is coming in, things go wrong. Like the line haul may not arrive, and then you already reserve space in some vans for whatever is in that line haul that didn't arrive, and you're kind of wasting a little bit of your capacity by doing things like this. or you may get packages that you didn't expect, and so on and so forth. So there are all sorts of uncertainties, and sometimes that's an even harder problem. It's because sorting takes so long. Sometimes it's the case that people can keep ordering packages after the sortation process has started. So basically, like there is no way of knowing in advance what is everything that will arrive, because some of those things are decided after you actually started sorting. So this is a planning for expected packages is a very fragile thing. What we tend to do instead, in particular for these very dense plans, is to actually introduce a buffer to basically delay the decisions that we have to make. So instead of sorting to the route directly, what we do is before we start sorting, we take the entire jurisdiction of the station and we split it into what are called zones. These are very, very small sub areas of the station, so small that everything that you expect to arrive to that area would fit in a single bag. And this is what this picture is showing here. There's a wall of bags. Each one of those bags corresponds to a zone. And what happens is, as packages arrive at the station, based only on their geography, on where they are, you kind of know which bag they should go to. And a typical bag would have like 20 shipments or something like this. So you get this, you receive all the packages to your station. There will be like thousands of bags at your station at that point. After you receive all the packages, the word that is normally used is after you induct all the packages, now you know everything that is at the station. At that point, only do you run route planning. At that point, you basically run routing. And what routing decides at this point is not which individual shipment will go to each route. It has to decide which bags will go to each route. You still have to sequence the bags. You still have to sequence the shipments within each bags. But your granularity of work is a bag rather than being an individual shipment. The main advantage of this is that then transferring the bags to the vans is actually a lot cheaper in terms of, it's a lot easier in terms of a physical process than transferring individual shipments to the van. So instead of like moving 200 individual shipments, you can move 20 bags. And that's a much easier process to do. So you can do this a lot quicker. So you basically receive everything to bags, wait into the morning when everything has been inducted. Then you run route planning, and then you pick the bags to individual routes and you run the routes. The disadvantage of this is that it imposes extra constraints on routing. Like now you have to take entire bags at a time rather than take individual shipments. So that may create a little bit of headroom in each route. And even when sequencing the shipments within each route, you would like to simplify the work of the driver. You don't want to be hopping across different bags. You want to do one bag, then go and do another bag, etc. There are exceptions to this, but this is the general idea of what we do. And this is just one of the processes. This interaction between sortation and route planning is one of the interactions that we have to worry about. There are a lot of other decisions that are important. There's a network planning decision, which is deciding like what part of the what is the jurisdiction, what is the area served by each individual station. That's something that we have to decide. Labor planning, which is we have to decide how many drivers and how many sort associates, how many people that work at the station itself do we need on any given day, given the volume that is expected. Sortation planning that I already talked about. Dispatch planning, you have to decide the order in which you dispatch the routes, how much work to dedicate to people that are doing those dispatches, and so on and so forth. And all these decisions are interdependent. So this is kind of designing algorithms that kind of work well and fit well with the process becomes very challenging. So
Renato, I have another question, if I may.
Yes.
So these bags, everything's interdependent. How does it happen that everybody's like, oh yeah, let's let's set up a whole bunch of bags in every station, right?
Yes.
That's quite a commitment, isn't it?
Yes. So actually what happened is Amazon was actually working on this expected packages, the sort to route environment, and it really wasn't working. So there was like the leadership at the operations level came up with a large scale company wide project to say like, can we design another process that would work better? And this is how we got to this zone-based routing, which is this idea of sorting to bags. But yes, it's a commitment. It was tested on one station first. When people said, okay, this is working, let's expand to more stations. It took years for this to become the standard that it is now.
Thank you.
So last thing before I get to performance is perhaps the most challenging of all, which is the fact that the optimization problem that we have to solve is very special, because the output of this optimization problem is essentially a list of instructions that a person will have to execute, or those are suggestions for a person to execute. So there is always a human being at the end of this, and human being had very strong opinions. So we actually have to create plans that not only look good on paper, that have the right numbers with them, but actually feel intuitive to the people that are executing them, and to the people that are supervising the people that are executing them. So I like to say there are many auditing opportunities by multiple stakeholders. So there are drivers and operators at the station, and leadership, like all these, the routes that we create, there are systems where people can go and look and see if the route makes sense or not. So, and that is very challenging for us. Our plans need to be efficient, but they also need to feel efficient. And people have very specific ideas of what an efficient plan looks like. So they want their routes to be compact. They want their routes to be well separated. So they don't want routes to overlap that much. They want routes to be clustered by provider. So you want kind of all the routes for one particular provider to be in this area, another route for another provider to be in that area, et cetera. You don't want your routes to be all over the place. You want your routes to have a sequence that feels natural, that it's kind of almost linear. So you go from one place and you keep going in a certain direction, rather than going to one place, then going somewhere else, and coming back to where you were, and then going to a different location, so to a different neighborhood, and so on and so forth. You want your routes to be consistent across days, so you want your route to look the same or very similar day over day, etc. And these are kind of feel like natural things to do, but if you look, for example, I have the optimal solution to that instance on the right, and here we're trying to do some sort of like knapsack together with we're trying to do a bin packing together with the routing, and it turns out that if you look at this highlighted area in blue here, there are like 4 different routes in this very compact area here. If you show this to an actual driver, to an actual operator, they say like, this is wrong, this is bad, you don't know what you're doing. This is the optimal solution, mind you, to the problem that was given there, but it doesn't feel optimal, and people like don't like these kinds of solutions. So we have to kind of worry about how to find a balance between those things. And in defense of the people that are asking for this thing, it makes sense, like that they want these kinds of abstract properties from the solutions that they have. You can think of them as all being proxies for efficiency and for robustness in some sense. So they want a plan that is easy to recover from. Like, for example, when they said they want all their routes for the same provider to be together, it's because if one driver keeps falling behind, they can send another driver to rescue them, another driver to go and pick up a few of the packages and help them out. If your drivers are all spread across the jurisdiction, it's going to take a while for them to go and find the other drivers, so that's bad. You want your routes to be compact for the same reason. Like, so if you get to a part of the route, and for whatever reason you cannot deliver at that time because there's some traffic accident or something that prevents you access to that, you can go do something else and then come back. If your route is kind of very spread out, coming back to that area is going to be hard. So they're kind of like worried about the real world, and they want our abstract solution to kind of be a good fit to that real world. And they will change if they feel like the route is not what they would like it to be. Drivers have no problem actually going and doing things in a different order and changing the way we do things to fix what they believe are mistakes that we made while planning, and what are often real mistakes that we made doing our planning, because we don't have a full grasp of what the reality of the world is for that particular location. So drivers will fix our mistakes all the time. So, and the biggest challenge for us is finding the right balance between all these objectives that people, these intuitive objectives that people have. So we have one non-negotiable, which is safety. Like we're never going to send a driver in an area that like to make an action that is not safe. Like there's a certain kind of turn or crossing the street or making a U-turn in a certain area. If that's not safe, we're not going to do that. But among all the safe options that we have, what is the best option to present to the driver? That's the challenging part, the most challenging part of what we have to do. So let me finally get to the part that is more related to performance and optimization. So that's a big challenge, which is scaling. So it's a huge problem that we need to solve. As I mentioned before, state of the art, just so maybe a couple of hundred instances with a couple of hundred shipments to optimality. In our case, each route may have a couple of hundred shipments. The entire problem may have more than 150,000 shipments. So it's a completely different scale than what is the state of the art in the literature for exact algorithms. So like basically there's no hope that we're going to do anything that is exact. The other thing is we only have a few minutes to solve the problem. So because again, remember that we first sort everything to bags, then we run route planning, and then we immediately start picking things to bags. So route planning is in this critical path for the process, for the execution at the station. So think like we have maybe 15 minutes to solve the problem in the best way that we can. At that scale with 100,000 shipments, it starts getting to a point that like it's not even the NP hard part of the problem that is complicated only. Even if you just want to get the inputs and say, oh, the first thing that I need to solve a vehicle routing problem is get a cost matrix that tells me like what is the driving time between any 2 points so that I can do the optimization for that. That will be 100,000 by 100,000 cost matrix. That is like extremely large. It'll be a 10 gigabytes just of the cost matrix, let alone the cost to actually compute this. So as Christian mentioned, kind of, I worked in the past in algorithms to solve routing in the sense of shortest paths problems on road networks, and those kinds of algorithms, not only from my team but from all teams, many teams across the world, are really important. They're really essential for us to be able to even start looking at the vehicle routing problem, at the NP-hard problem that comes after that. So we do need to use these state-of-the-art algorithms just to prepare the input for the problem that we need to solve. Once we have the inputs, what we actually use is a combination of mathematical programming plus combinatorial heuristics. I'll talk a little bit of this, more about this in the next slide. And as I said, there's no way we're going to do global optimality, but finding a clean solution to the problem is important. So we're not going to find a globally optimal solution, but we should find something that looks locally optimal so that it doesn't have anything obviously wrong for all the stakeholders to look at. So a couple of words about performance in terms of like what we learned. From the point of view of algorithms, I think the main tenet that we have is that speed is quality. Because we're solving an NP-hard problem, we kind of have a fixed amount of time that we can use. And the better the performance that we have, we're not going to spend that on having less time. We're going to spend that on having a better solution. So whatever it is that we're doing, we will, the better the implementation, the better the algorithms that we have, the more iterations we can do and the better the quality of the solution that we have. The way we solve the problem is basically modeling this as a set partitioning problem. So we essentially create a bunch of candidate routes with a subset of all the shipments that we have. We assign a cost to these candidate routes, and then we essentially have to find a subset of these candidate routes that covers all of the shipments that we need to deliver that has a minimum total cost. So that's like the very simplified version of the problem that we need to solve. And one of the techniques that we use that has been very important is this idea of iterative refinement. So essentially, the number of potential candidate routes is, of course, kind of very large, it's exponential. So like we have to focus on routes that are, to start, we just focus on a very small subset of the routes that have a lot of structure to them, knowing that we're going to lose optimality by focusing only on those routes, but we have a problem that we know that we'll be able to solve. So we start by solving a simplified version of the problem with a very small subset of all the potential routes that we could look at. And from there, we start doing refinements to find a better one. Another thing that we do is we mix and match techniques. So it's often tempting, in particular, like in organizations that are very focused on the operations research size of things, that you can create all these candidate routes, you throw them, you formulate the problem as a mixed integer program, you throw them at a solver, like we use Express here, and you hope that the solver is going to find the best solution to that particular map. This works up to a point, but once the problem starts being big, that doesn't work that more. And it kind of fails in very bad ways. It's not like, oh, you start having an optimality gap of like 0.5%. At some point, you get from having an optimality gap of 0.5% to have an optimality gap of 95%. And then the solution is completely unusable. So what we do is we use these techniques, but we don't rely on them to finding a reasonable solution at the end of the day. Like we always have backups. For example, we solve a linear program, which is usually pretty quick, even with a large number of routes. And we have some rounding techniques in order to kind of transform this into a feasible solution. We have constructive heuristics as well. We have a dynamic programming based local search heuristic as well. So together, these things are very robust in the sense that they will always find a very reasonable solution. They're not guaranteed to find an optimal solution by any means, but they're guaranteed to find something that we can work with. Another technique that is very important to us is kind of a lot of pre-processing. So one way to think of the problem that we have is, oh, we have this vehicle routing problem. We transform this into a set partitioning. So there, all we need to do is solve a partitioning problem on candidate routes, and each candidate route by itself is a TSP. So it's a traveling salesman problem. So it's an NP-hard problem by itself. So, and we have to solve tens of millions of small NP-hard problems rather than solving one large NP-hard problem. So that doesn't really help that much. But by using a lot of pre-processing, by recognizing that you're often creating different candidate routes in the same area for similar drivers, we can do a lot of pre-computation. For example, we have to work with the bags. So what we can do is essentially pre-process all the ways of servicing a bag, like multiple TSPs to go across, multiple paths to go across each bag. And then when we create a candidate route in that area, we essentially just concatenate these partial solutions, choosing which of the previously selected sequences to use in each one of those bags. And it turns out you can use dynamic programming to do that, which is a lot faster than trying to create a new, even heuristic solution within each bag for every iteration of that. You can reuse routes that we create for one type of driver for other kinds of drivers, et cetera, et cetera. So other things that we do often is we try to optimize the code as much as we can with a very large caveat that you see right at the beginning. Constants matter, and we do our best within the existing constraints. That said, most of the code is in Java, which was surprising even to myself. So basically, we use Java because it is what all the tech teams around us use. And we thought that, of course, a native language would be faster, but there will be so much overhead in communicating with our sister teams and so on and so forth that it's worth for us eating the performance cost years to make us more agile and for us to be able to kind of do development better. If you do Java with reasonable amount of vigilance and discipline, we can lose only a factor of 2 or 3. And I take that as a personal challenge rather than kind of complain too much about this. Like in my previous jobs, I used to do everything in C++, and then whenever I needed to do a tech transfer, it was a pain. By doing everything in the language that the other teams use, it actually makes it a lot easier to kind of put things in production and get faster in terms of getting the changes that we make realized. We have to be careful. We use primitive types whenever we can. We have to be very careful with garbage collectors. So like we avoid long-lived short objects whenever we need to allocate stuff. We try to allocate large objects. We try to make the object short-lived. We do a lot of parallelization, but coarse-grained parallelization to avoid the communication overhead and so on and so forth. If we are careful, if we're vigilant, things work reasonably well. Another thing that we do is we focus on bottlenecks. We kind of find parts of the problem that are in the inner loop that we have to do, and we kind of go and optimize those. Like for instance, one thing that we do a lot is evaluate a route to figure out what is the cost of that route that needs to kind of traverse individual elements of that route. We created our own library to do this in a faster way. We do our own like memory management, and we reuse objects and so on and so forth. So that's important. The flip side of that is that we have to know when to stop optimizing. So they're coming from the algorithm engineering background. There's always like you always look at a problem and say, I could make this 20% faster with some effort. But sometimes you look at this and say, I could make it 20% faster, but this module is already taking like 0.5% of the entire execution. Let me look at other places where like I could invest my time better to find something. And this is the last point here, which is optimizing beyond optimization. So bottlenecks are often not where you expect them to be. So there was a time where the entire NP-hard, solving the NP-hard problem took as much time as gathering all the inputs that we needed to solve the NP-hard problem, which was, of course, like polynomial time to do that. So sometimes we have to go and kind of work with other teams to make sure that every aspect of the problem is as fast as it can be. And sometimes that's not where people would think the bottlenecks are not what people would think they are. So last slide, no, kind of almost on time. Overall lessons, even beyond performance optimization, we can presume to know everything. It's very important to keep agility and flexibility and extensibility in mind when developing algorithms for these hard and complicated problems that keep changing all the time. We really avoid over-designing for the current state because we know that tomorrow people are going to be asking for something different. So we try to keep things open-ended, as optimized as we can, without making it such that it's very hard to add a feature or to change the way we do things. We have to be very robust. We have to always produce a reasonable solution, no matter how bad the inputs are, no matter how bad they were set up. The inputs will be imperfect. Instead of failing the entire plan, sometimes we'll unplan individual packages or do our best effort so that operationally people can deal with that. So the worst thing that can happen is that there's no plan for that particular day. Then people are not going to get their packages. As I mentioned, local optimality is crucial for trust. We're not going to ever find the optimal solution to what we're doing, but we have to find solutions that look reasonable to all the human beings that are looking at them. And finally, we always try to listen to our customers. And our customers are mostly drivers in this particular case, also other businesses and so on. But at the end of the day, the driver is the one that will have to execute this. And they will deviate from our plans. We're never going to create perfect plans, but we take their deviations as a hint to us that we could have done better. Like so, and so what we do is we generate a good recommendation, but we're not prescriptive. They're encouraged to deviate from the plan if that's the best thing, if they think that's best. Our success is creating a plan that people don't want to deviate from, and that's how we measure ourselves. And with that, I think that's it. Thank you.
Thank you very much, Renato. It's 1 o'clock, and I think we can take a few minutes to hear questions from anyone in the audience.
Maybe you want to go first, John.
John, you're raising your hand. Please go.
Yes. Firstly, Renato, thanks for an excellent talk. It really got me to thinking about a number of issues. So thanks for just a great job. One issue is that you have a very precise model. You showed us all about approaching the house from this direction and that direction.
Mhm.
I'm curious about how your model relates to real observed times. There are all sorts of stochastic issues. If there's an angry dog in the yard one day, it may not be there the next day, on the one hand. On the other hand, if I'm expecting something and I walk down my long sidewalk to greet the driver, I've sped up his time. So the question is, how does this incredibly precise model you have relate to the real times? You mentioned before that in the algorithmic issues, you vary from, within a 0.5% of optimal to 95%.
Yes.
So you lose some there. But
Yeah.
if you get this perfect solution to this precise model and reality is different. So I'm
Yeah.
worried about that, how you verify it. Can you
Yes.
learn? Can you look at predicted times versus observed times? So
Yes.
there's a cluster of questions there. Choose anyone interested to you.
Yes. So to be clear, my team is very narrowly responsible for the optimization part of this, but there are entire teams that are responsible for essentially figuring out the inputs, and that involves like even the service times that I mentioned. That's a huge part of this. That like there is a distribution of like looking at the past and looking at the similarity between different addresses. How have people done? And of course, like when we plan for a certain kind of point in that distribution. But we do consider also the fact that there is inherent variability within that distribution, and that is actually accounted for. So like when building the entire route, some of those things would kind of offset each other. Like some stops will be faster than they usually are. Some stops will be slower than what they really are. At the end of the day, you're going to see something that is more or less what you expected. But there is constant monitoring for people, like where people are checking, like are we underestimating? Are we overestimating how long people take on this? What kinds of adjustments can we make to the estimations so that we have more realistic times, so that actually reflects what drivers can actually do under those situations. This is for time estimation, even for things like location, like deciding where a house is and how it relates to the road network. Even that can be very imprecise. And we are even routing to a specific point in the road network. There's no guarantee that people are going to be able to park there. So there are learning systems that essentially say, oh, where have people parked in the past around this area? Can we try to guide our algorithms to go to areas where it's more likely that they will find parking, and so on and so forth. These are all kind of things that we have to worry about when doing these optimizations.
Thank you.
Thanks, John and Renato. Renato, I want to let you know that the chat line is just ringing with applause for your talk. And we're a little bit over time. I want to just do one last check-in and see if anybody has a quick final question. Otherwise, we will close, but any final questions for our speaker? Put it in the chat. I'm not seeing anything, so I think I'll take that as a cue to say this concludes our Fast Code seminar for July. Thank you very much, Renato, for a fantastic talk, and have a great rest of your summer, everybody. The next Fast Code seminar is going to be in September. Take care.
Thank you. Will the room be open for a while? Can we stay and chat, or are you closing down?
I'm going to close the meeting.
Thank you.
Yep. Thanks for asking.
Thanks
Thanks again,
Renato.
Renato.
Thank you.
Bye-bye.
Bye.